Okay, on this problem, I've got a tapered shaft, length L, radius R, blah, blah, I got all this stuff, okay? I'm trying to find the angle of twist of A of this guy. Now, I've got to change in the radius as I go down, so I can't just use the typical TL over JG, but what I can do is use the most general form, which I'll go ahead and write down here, which is going to be the integral from 0 to L as I move down the length of the shaft, okay? And that's going to be the torque as a function of x times dx all over j as a function of x times g as a function of x. Now for our situation, the torque is constant, right? It's the same torque through the whole shaft. It's all of the same material, right? It's homogeneous material, so g is going to be constant, so I can pull those out. What changes is the polar moment of inertia as the radius changes as I move down that shaft. So let me rewrite this, pulling out my constant pieces. So I pull out t and g like so, integral from 0 to L, and that's going to be dx all over j as a function of x. So that's really what I need to find, is what is j as a function of x. Okay, well, we know the polar moment of inertia is pi over 2 times the radius, and the radius is what actually changes to the fourth. So that radius is a function of x. So now the question becomes, what is the radius as a function of x? Well, it's a linear slope. Again, it starts at 2r, ends at regular r as I move through that out. So that slope, the radius changes r over that L. So the slope is going to be r over L. Okay, so let's just start rewriting that. So pi over 2 is constant. That stays there. Okay, and again, when x equals 0, that's at the wall there. That's when x equals 0. Okay, that's going to be 2r. And then the radius shrinks, right, as a function of r over L. So minus, because it shrinks, r over L times x. So again, when x equals 0, it equals 2r. When x equals L, which is when I'm at A there, then it's 2r minus r, or just r, which is what it is. Okay? So that whole thing will be to the fourth, like so. Okay? So I just get the equation as a function of x for that polar moment of inertia, which is what I needed there. Now, I take this, plug it back into that top equation to find the angle of twist, which is kind of ugly. So it's t over g times the integral from 0 to L. Okay. Now, j as a function of x is pi over 2 times 2r minus r over L times x all the way to the fourth. Okay. And then that times dx. Now, I am not very good at calculus. Okay. So I'll let you do the calculus on your own. It's not a calculus class, it's a strength of materials class. But, or you can use a calculator if you've got that, which is what I did. And I get the following. On the denominator, I get 12 pi g r to the fourth. And on the numerator, I get 7 t times L. And again, you'll have to do the calculus on your own or plug it into your own calculator if you want to prove yourself to that. But what is most important is setting that integral up. Again, recognizing t and g are constant. The only thing that's really changing is the radius, therefore the polar moment of inertia is changing. So just finding the equation for that radius as a function of x as I move from, B to A, okay, getting that equation, then I can plug that in, do the integral, and find what the angle of twist is for the end A in this situation.